again, we need to modify the right-hand side. And actually, we usually assume that each of these additional variables, which are called slack variables, they are non-negative. So let's assume we have new slack variables, let's call them u, which are non-negative. And what do we need to do here? We have to subtract ui here. Okay? So by this, we are giving the optimization problem additional freedom to violate the constraints if it is necessary. The only problem now is that the optimization will now start violating the constraints as much as it wishes. Okay? In other words, if we would just solve this problem, then even separator like this would be fine. Because what it said is, well, you allowed me to violate some constraints, so I just did that. Okay? So now we have to do that additional thing which says we have to minimize the number of violations. And if you remember from the previous lecture, there was one kind of cheap trick which, if not directly minimizes the number of non-zero components, it at least it at least gives us a good approximation of the number of non-zero components. Because clearly, if all constraints can be satisfied, like all original constraints, then both of these variables here would be zero. So any non-zero value of these slacks here means the corresponding constraint has to be violated. If we want to minimize the number of violations, we have to minimize the number of non-zero elements in these vectors here. So what was the cheap trick to indirectly minimize the number of non-zero components of a vector? Yeah?
Absolute value.
That was the absolute value, and if we have a vector, then it's the one norm of the vector, which is just the sum of the absolute values. In other words, again, we have these vi's, and remember this I goes from 1 to m in this line, and here it goes from 1 to n. Okay? So what we will do is we will denote by v the whole vector of slacks, so v1 to vm, and u would be u1 to un. Okay? And then to indirectly minimize the number of non-zero components, we would minimize the one norm of v plus the one norm of u. Okay? So this will indirectly minimize the number of violations. It is not the exact answer, but it is a very good approximation of the answer. And now what I would like to look at is here, together with these conditions, and think, can this maybe be simplified even more? We know that the one norm of a vector is the sum of the absolute values of the individual components of the vector. Now, we know that all slack variables are non-negative. Do we still need the absolute value there? No. We can equivalently replace this by minimize the sum of v's plus the sum of u's. It is the same problem. Really, because we are assuming that those additional variables are all non-negative. But this is somehow simpler representation because we know that to model the one norm, we would need to introduce additional epigraph variables. It would just complicate the problem. So essentially, what we have obtained is a cost function. Can we classify the cost function maybe? What kind of a function is that? Remember, the optimization variables now are A, B, as previously. But now we have additional optimization variables, which are these vectors of these slack variables. So what is the cost function? What is the type of the function? Is it a linear function, a quadratic function, a non-convex function? What is it? That's just a linear function, right? Because all the multipliers here are 1, and we are just summing them up. Okay? So we are going to minimize a linear function subject to those constraints, A transpose xi plus b larger than. Actually, I can normalize that, so we can do the same trick as before. Plus sorry, it should be minus ui, and here it would be A transpose to yi plus b less than 1 plus vi. Okay? So that's the final problem that we have to solve. And this problem clearly is a linear programming problem because we have a linear cost function and all constraints are linear. Now, if we want to convert it into that very standard form, then we would need to find out, again, what should be the matrices. So here what we would do is we would move all optimization variables to one side, all constants to the other side. We would convert these inequalities into the standard form, and then we can find easily what these matrices should be. Again, you will be doing this in the exercises. Okay. So that was the approximate separation. And now comes this fancy term, support vector machines, which is basically the combination of approximate separation and a robust separation. So essentially, if we would like to have a robust strict separation, this is the answer, right? But this separation maybe is not really the best in the world. Essentially, what if this point was just wrong measurement that in fact belongs to the red set? Okay? We would like to find a separator which is simultaneously robust and simultaneously minimizes the number of misclassified points. In other words, we would combine these two things together. Okay? So essentially, this is a very good separator. Even though it misclassifies one point, for the remainder of the points it is very robust. While here, no misclassified points, but very low robustness of the separator. Okay? And support vector machines are a way how to find a separator which is both robust as well as minimizes the number of misclassified points. And yes, as you have already guessed, we just combine those two things together. Okay? So the first thing here, by minimizing the 2 norm of A, we know that we maximize the robustness of the separator. The other thing is from the approximate separation where we indirectly minimize the number of wrongly classified points. And the constraints are the same as for the approximate separation. Now, this problem, technically speaking, is a so-called multi-objective optimization because we have really two objectives. We would like to maximize robustness and simultaneously minimize the number of misclassified points. So we have two objectives that we would like to kind of minimize or optimize simultaneously. And these kind of problems, multi-objective problems, they are actually very difficult to solve. And a standard way how to convert these multi-objective problems into easy problems is to do something which is called scalarization. So in scalarization, what we do is that we merge these two cost functions into a single cost function, and we use a scalar parameter which says how much do we care about this term and how much do we care about this term. Technically speaking, we could have two parameters like gamma 1 and gamma 2 here, but since they are just constants, we will normalize the coefficient here to 1, and we are just left with this gamma. Okay? So I'm going to ask you, what if I choose gamma large? What will happen? Will it be a robust separator or would it be a strict separator? Why?
Because we penalize the number of misclassified points more than...
Precisely. So the emphasis here is really on this term. This term, the minimum is at 0, and it's at 0 where all points are strictly classified. Okay? However, gamma small means robust separator. Okay? And gamma, somewhere between this large and then the small value, gives like larger emphasis on one side or the other side of the problem. And in the exercises, you will have a bunch of time to play, essentially, and see what is the impact of the choice of this gamma on the performance of this separator. And these kind of support vector machines, they are very frequently used in practice. Essentially, the whole or majority of the field of artificial intelligence is about support vector machines. And support vector machines are just fancy word for separation which can be solved by linear programming. So essentially, artificial intelligence is about optimization. Okay? So one option where these support vector machines are frequently used is where they want to detect objects on images. So essentially what they take is a bunch of samples, so they want to detect a person in an image. So they create these kind of frames where they say this is a positive sample and all other samples are negative. So here we have one negative sample and here we have another negative sample. And they, of course, create a bunch of these samples, and then they just find a separator which says, is there a person on this image or is there no person there? So you can imagine that it's really these two set of points that we are trying to classify. Okay? So for that, we can use the support vector machine because it would simultaneously be robust, because you can imagine each person would be dressed differently. So we cannot really use strict separation, and we would like to use approximate separation such that we minimize the number of wrongly classified samples. So that's what they do in image recognition, and actually the path from the picture to those data points which we are classifying, it's actually quite interesting. So what they do is they first do rastering, so they divide it by a grid. Then they perform something which is called feature detection, so like detecting like what are the important aspects of each of these grid grid cells. And then these features are those which represent those data points, and then they just use linear programming to find the separator. So you can build your own CIA just using convex optimization. So that's one example of where these kind of techniques are used. And they are used really, really frequently in practice. So for instance, to classify proteins, they use it in biochemistry. Very frequently, support vector machines are used for character recognition. So when you have handwriting or even like scanned image and you want to do optical character recognition, inside, what is being done is that the algorithms are being trained on a set of data, and based on this data, they devise a classifier which says, is this the digit 5 or is it not? Okay, and then they have a bunch of these separators essentially for each character. But then internally, it's doing support vector machine classification. Spam detection is a wonderful example of where support vector machines are being used. So we have a bunch of features like title missing or title available. Okay, if the title is missing, either the person is lazy, but very often it indicates a spam. But it is not the only indication of a spam. So there are multiple other criteria which have to be satisfied for something to be spam. And we see that we really have at the end only two sets of points, legitimate email and spam. And each of those data points have different values of those data points. So the first axis might be whether the title is there or it is missing. Then it's this HC value, which I admit I have no idea what it really means. So it's yet another axis on our set of data points. So basically, very good spam filtering internally does optimization. Okay? This optimization is done offline. That's the training process. And then online, it is just evaluating those separators. So new mail comes, we take new measurements of these values, of these features, of these properties, and we just check whether the point lies to the left or to the right of the separator. If it is to the left, it is a spam. If it is to the right, it's a legitimate email. Of course, we might retrain that separator, which requires solving a numerical optimization problem, but that can also be done. So these are just some of the very few examples of where these kind of separation techniques, especially support vector machine techniques, are used. Nowadays, support vector machines is treated as a technology. Okay, so when you want to classify something, you try support vector machines first, because it's like combining everything what we have seen so far. Okay? Robust separation, approximate separation, linear one, and so on. Sometimes, however, this requirement of having a linear separator is quite restrictive. So here we might use support vector machine which would find something like this, which would minimize the number of misclassified points. But why not to use a nonlinear separator which provides a strict separation here? Okay? And actually finding this separator might be easy, and it might also be very difficult. So for instance, if we are separating by a quadratic function like the ellipsoid here, it's quite an easy problem. Even finding such a separation function sometimes is easy, but in general these are very difficult problems. So essentially the problem that we are looking at is the same as before. Also we started in the linear separation by saying, let's find the separation function which is positive on one set of points and negative on the other one. And in the linear separation, this function f was a linear function. Now this function f can be an arbitrary function. Okay? And we need to find what the function is such that it satisfies these constraints. Now the problem is that if this is a nonlinear function, we have nonlinear constraints. And actually that's why we have looked only at linear and quadratic programming, which both have only linear constraints, because those problems we can solve easily. Problems with nonlinear constraints are very difficult to solve, and we don't even know whether we have found the best possible solution or not. So we would like to avoid solving problems with nonlinear constraints, because we have no guarantees of solving those problems effectively. However, there is a kind of an exception to this bad news, and the exception is that if this separator function is the sum of these fk's here are so-called basis functions, and these alphas here are the multipliers. What we mean by that is that imagine that we would like to separate two sets of points by a polynomial which is something like this. At the first sign, it appears that this is still a difficult problem, because what we then need to do is we have to add this to the constraints, once being larger than 0 and the other time being smaller than 0. Okay? And we just said if we have nonlinear function, it's a difficult problem. But actually this problem is very easy. Why? We have to realize what are our optimization variables in this case. What are we optimizing? Are we optimizing these z's here? No, these z's are our measurements. These are just constants. What we are optimizing for are these a's here, these multipliers of those individual powers of z. This is a linear function in those decision variables. So that's why even nonlinear separation, if we assume that the separator function can be written as sum of some multipliers times basis functions of individual data points, then this is an easy problem. Because the optimization variables, they enter linearly, despite the fact that we have some nasty nonlinearities here. So we might even have like the basis functions which are, for instance, sines or cosines. Doesn't matter, because these are just sines and cosines of constants. Okay? So these terms here, which appear to be nonlinear, they would just be constants, and we are left with linear constraint. Okay? So that's why if we can split the separation function into this form, we can actually solve the problem very easily, just by linear programming, okay? Or maybe by quadratic programming if we then require maybe robustness and stuff like that. Okay? Though robustness here is not so immediate, because the the width of the slab is no longer proportional to the 2 norm of A because we don't have just a linear function. Okay? But the whole reason why we are assuming nonlinear function is that we get a strict separator no matter what. And one fancy example of this technique that I have found is a system. Actually, this is an image from a patent application. A company has developed this kind of technique to determine the gender of a person from the image. So essentially what they have done is they have taken the pictures of 200 people, and they knew which of them were females and which of them were males. And then they were extracting the features from those individual images, and here we have just 2 principal features. I don't know what they really are. They might be like the size of the nose or the position of the ears or something like that, okay? And then what they said is that really there is like a distinctive difference between males and females, which cannot be captured by any linear separator, but actually there is a nonlinear separator dividing these 2 sets of points, meaning males and females, and it gives very good results. So essentially then the technique would just be take the picture, extract those features, and just evaluate those data points with respect to the separator. If it is to the left, it's female. If it is to the right, it's very probably a male. Okay? And yes, then they can also maximize the robustness. I mean, we can do plenty of stuff here. Okay? And here they are using polynomial separation, which is easy. Okay? We might also use some other, like general nonlinear separator functions that would be more difficult. So let me wrap up the first part. So what we have covered today is separation and classification. Really, there is no difference between these 2 words. Well, there is. Classification can be between multiple sets of points, but at the very end, it all boils down between separating one set from the other set. And we have covered several approaches to achieve this goal. A linear separator, where we don't care about where the separator is, as long as it is a strict separator. We had the robust separator, which is really good in like avoiding or increasing the robustness of the separation scheme. Approximate separation allows some separation constraints to be violated, but then we are indirectly minimizing the number of wrongly classified points. Support vector machines were a combination of robust and approximate separation, and we can extend all those procedures also to nonlinear separation. So I invite all of you to come for the exercises and really try it out in practice.